Space has always beckoned man with its mystery and unpredictability. However, its vast expanses beyond our home planet have proved too harsh and dangerous for us. The freezing cold, deadly radiation, and devastating vacuum have become serious obstacles in our endeavors to reach other planets and stars. That's why we've built spacecraft that can operate in the harsh conditions of outer space and reach distant celestial bodies. And today, it's time to embark on a fantastic journey with them. Our journey will begin on the most explored planet in the solar system, Mars. Then we will visit the majestic rings of Saturn and find out what happened to the spacecraft that explored them. After that, we'll travel to some of the most spectacular of the many satellites we know, the misty Titan and the blazing Io. Following the indomitable space travelers, we will get to the far reaches of the solar system to meet the dark and mysterious Pluto. After that, a long journey through the cosmic abyss awaits us, along with the intrepid Voyagers. After traveling several light years in the blink of an eye, we will reach an amazing system called Alpha Centauri. And at the end of our journey, we will visit the nearest known stars. Let's get ready, and we begin.
Kosmo.
The first in outer space. This is Mars. That's what it is believed to look like several billion years ago. Heat and liquid were trapped within the dense CO2 atmosphere the planet was shrouded in. Numerous rivers used to flow on its surface, and most of its northern hemisphere used to be covered by water. However, all this was to vanish, leaving behind only traces on rocks. It is thought that the weak and unstable magnetic field of Mars failed to protect it against solar wind. In hundreds of millions of years that followed, its atmosphere gradually deteriorated, with water vapor breaking down into hydrogen and oxygen. The lighter gas rose up into the upper layers of the atmosphere to float away into space. As for oxygen, it reacted with rocks, which gradually led to the planet getting tarnished by rust and sand. A thin layer of orange dust and perpetually frozen ground. That is all that remains of the great abundance of water on the red planet. To have a better understanding of what is currently going on Mars, we will first have to look in its depths. Thanks to the sensitive seismographs on board the InSight probe, which have been exploring the inner makeup of the celestial body for 4 long years, scientists have some ideas about the processes running in the planet's depths. At the very center of the planet, we can observe a large and massive core of iron, sulfur and nickel. Its radius is more than half the size of the entire celestial body, and its temperature lies between 1800 and 2000 Kelvin. Because of the enormous pressure, most of the core is in a solid state, and therefore incapable of producing a stable magnetic field. The core of the planet, in its turn, is surrounded by a layer of molten mantle about 1,500 kilometers thick. Its composition is heterogeneous and depends on its depth. The lower layers contain various metal oxides, while the upper ones are composed of olivine and silicates. On the outside, the mantle is bound by a massive crust, the average depth of which is estimated to be about 50 kilometers. This is 5 to 10 times greater than the parameters of our planet's oceanic lithosphere, and comparable with the thickness of the Earth's continents. It is also noteworthy that in the northern hemisphere, the Martian crust consists predominantly of andesite and in the southern hemisphere of basalt, which may indicate that it was formed at different times. Decades of observation have yielded hundreds of thousands of images of the surface of Mars. By putting these together, scientists have been able to produce an incredibly accurate and detailed map of the celestial body, containing many objects. Some of them are quite small, while others stretch for thousands of kilometers and can be seen with telescopes even from Earth. And one such region of interest is Valles Marineris. This gigantic system of intertwining canyons and chasms stretches along the planet's equator for 4,500 kilometers. Its western part is deeply cut by the immense volcanic Tharsis Plateau, and our plunge into the Great Rift will begin almost in the center of the giant plateau. It is here that the unique and mysterious region, marked on maps as Noctis Labyrinthus or the Labyrinth of Night, is located. It is an area of chaotic terrain, stretching 1,200 kilometers from west to east. Here, numerous deep, steep-edged drifts intersect multiple times, dividing the surface of the planet into irregularly shaped blocks. The top is made up of softer, lighter sediment, heavily eroded, while the base is made up of solid bedrock. Over billions of years, the slopes of the chasms have collapsed in many places, leaving behind numerous landslides. It is thought that it was here that precipitation that fell on the surface of the upland regions in ancient times accumulated together and flowed eastwards in unstoppable turbulent streams. Evidence of this can be seen in the traces of deep water erosion, seen at the bottom of most chasms, and in the layered structure of slopes and landslides. In addition, spectral analysis shows that certain minerals that require liquid water to form, such as hematite, opals and dian sulfates, for example, are abundant in this region. Observations show that Noctis Labyrinthus is periodically obscured by dense fog, meaning that it is still one of the most humid regions on the planet. It is thought that the water contained in the soil evaporates into the thin Martian atmosphere during the day, and the high walls of the gorges prevent the humid air from dissipating. With temperature dropping, the water condenses as microscopic ice crystals that slowly settle on the surface, forming a thin layer of frost. As one moves eastward, the bizarre interlocking chasms of Noctis Labyrinthus gradually morph into a system of giant canyons that occasionally intersect. Over billions of years, powerful streams of water dug deep channels in the Martian rocks, and then winds and sandstorms ate away at their slopes. But whichever path we take, it will eventually lead us to the giant Coprites Chasma. It is here that the deepest point of the Valles Marineris is recorded. It lies 11 kilometers below the surrounding plateaus. Calculations show that in ancient times, Coprites Chasma was a narrow and long running water lake, which when at its fullest was comparable in volume to the Earth's Black Sea. The region is believed to be one of the most promising objects for future research. The soil at the bottom may contain traces of ancient microorganisms, and its slopes are quite literally recorded pages of the geological history of the planet and are of great scientific value. As we continue along the canyon, we find that it gradually loses its steepness and gently dissolves into the giant Chrysoplanitia. Here too, however, we see traces of the water element in the form of rounded terraces and elongated islands, probably formed by sediment from Valles Marineris. Similar geological formations can be found on our planet in the deltas of major rivers, such as the Amazon and the Nile. Thus we have made acquaintance of one of the most tremendous and visible evidences of there having been water in the ancient eras of Martian history. However, the giant Valles Marineris rift has only been explored from space. The wheels of a Mars rover have never touched it. To get a closer look at the red planet, we will have to travel far to the east. after flying several thousand kilometers over unfriendly rocky deserts, we finally reach a large crater called Gale. About 3.8 billion years ago, a massive asteroid collapsed here, leaving a deep circular depression 154 kilometers across. At its center there is Mount Sharp, a vast irregular upland area composed of layers of sediment. In ancient times there may have been a large circular lake with a central island. In the present day, however, Gale crater is known as the landing area for the Curiosity rover. The story of this mission began almost 11 years ago when the Curiosity autonomous probe landed on the surface of Mars on the 6th of August 2012, a symbol of human determination and thirst for knowledge. The mission's goals included studying the planet's climate and relief, as well as searching for water and traces of biological life. Almost immediately after landing, the rover found evidence that the planet used to be much wetter in the past than it is now. The first photos transmitted to Earth clearly show a valley washed away by a torrent of water. The area has been dubbed Peace Valleys, meaning the Valley of Peace, and is one of the clearest instances of evidence of water erosion on the planet. Curiosity then headed east and soon reached a sandpit called Rock Nest. Here it took its first soil sample and found it contained around 3% of water. Next, the rover turned southwest and continued on its way. It crossed the rocky wastelands of the Glenelg region, where ruthless winds had crushed sediment down to bedrock formed more than 4 billion years ago. Then, climbing occasionally up rocky slopes, Curiosity reached the western end of the Bagnod Dunes, studying the sedimentary rocks, which are relatively recent in geological terms. From the desert, the rover turned south and set out on a long and tiring climb up the slope of a small mountain range called Vera Rubin. Along the way, the sand and silica under its wheels gave way to hematite, an iron oxide that only forms when in contact with liquid water. It turns out that the mountain range is largely made up of this substance, which means that in earlier times, the climate in this region was much more humid. In total, Curiosity stayed on Mars for more than 3,000 days, roughly 5 times the planned duration of its mission. Despite all the difficulties and obstacles, it traveled nearly 30 kilometers across the harsh Martian terrain and took 28 samples of alien soil. The probe's chemical analyses detected not only water, but also organic molecules including benzene and aromatic hydrocarbons, while its cameras beamed back to us thousands of photos and videos. Leaving the tenacious Mars rover behind, we will continue our journey and head southwest. Here, Hellas Planitia is one of the largest impact craters on Mars. It is thought that about 4 billion years ago, a massive asteroid with a radius of about 50 kilometers crashed into the planet here at high speed. The terrific explosion left behind a gigantic crater about 2,300 kilometers in size, and millions of tons of rock were crushed and ejected far beyond its limits. Some of these fragments may have reached outer space and then crashed to the planet's surface hundreds or thousands of kilometers away from the site of the cataclysm. It should be noted that at that time, Mars was likely to have been a friendlier and more favorable celestial body than it is now. The giant lowland area that appeared at the impact site was quickly filled with water, forming a large lake or a drainless inland sea. Over billions of years, it gradually shallowed and became what we see today. A huge crater, more than 7 kilometers deep. From a distance, the bottom of the basin may look smooth and flat, but this is just an illusion. In fact, it is covered with numerous small hills and fractures whose appearance is largely accounted for by the movement of layers of subterranean ice. Similar relief occurs on Earth, in Arctic barren expanses and permafrost zones. Due to its great depth, the atmospheric pressure in this region is about twice as high as the global average, resulting in unusual weather phenomena. For instance, from time to time, a misty haze forms over the crater, which is uncharacteristic of Mars. The wind carries some of the mist out of the crater, but its wisps quickly disperse in the thin atmosphere or settle on the frozen rocks. During Martian winter, the Hellas Planitia is entirely covered with frost and when seen from the Earth, appears as a large bright spot. Because of this, the area has long been mistakenly considered an upland, and it wasn't until the end of last century that its true nature was determined. Next, our route takes us to the north, to Jezero crater, which used to be a large running water lake in the past. The Sava River flowed into it from the north and the Neretva River from the west. Traces of these large water arteries are still to be seen on the surface of Mars. These appear as layered deposits of fluvial sediment and large scour marks on the mountainous walls. It was one of these regions that became the priority target of the Perseverance rover, which descended into Jezero crater on the 18th of February 2021. Originally, the rover was planned to land near the Three Forks area, in the Neretva River Valley. However, weather conditions shifted the landing point 1.7 kilometers to the southeast, and the rover was separated from its target by an area of impassable sand called Saturn. It was at this point that the unique Ingenuity helicopter got to show its worth. It flew over the surface of the planet and provided a wide-angle panorama of the ancient delta, as well as a unique photo of the Kodiak Plateau, 2.3 kilometers from the rover's landing point. Once the rover had settled in and reconnoitered its surroundings, it started out on a long, arduous journey around the unfriendly desert that separated it from its destination. Traveling south along the very edge of Saturn, the rover stopped from time to time to collect soil samples. At the same time, Ingenuity successfully completed flight after flight, beaming back to us many photos of Mars from previously inaccessible angles. On Mars Day 168, the spacecraft turned westward. The idea was to pass along the bottom of the crater, skirt the southern tip of Saturn, and reach a rocky ridge along which it would head north towards the delta. However, the terrain proved difficult and the rover was forced to turn back. Pretty much retracing its way back to the landing area, Perseverance set off towards its destination. After smoothly skirting the northern part of the desert, it gradually turned westwards. Eventually, after a long and arduous journey, the rover did reach the delta and began exploring it. This occurred in April 2022, 413 Martian days after it had landed. By now, Perseverance has traveled more than 18 kilometers across the unfriendly Martian desert. It has collected 15 soil samples and sent more than 166,000 images as well as gigabytes of data from various sensors. In addition, the MOXIE vehicle, which is part of the rover's science payload, successfully obtained about 100 grams of oxygen from the Martian atmosphere's carbon dioxide, which seems to reveal prospects for future colonization of the planet. At the same time, Perseverance's seismographs recorded several Mars quakes, enabling scientists to learn more about the internal structure of the celestial body. The Ingenuity helicopter proved just as useful. It has completed more than 50 flights by now, traveling a total of over 8 kilometers, thus convincingly proving that even in the rarefied atmosphere of Mars, it is possible to use aircraft for research and exploration. In addition to desert landscapes and rocky debris, Perseverance occasionally photographs the night sky of Mars. For example, this little white dot here is one of its satellites, Deimos. More recently, Perseverance captured Phobos briefly eclipsing the Sun. This unique observation was not just a spectacular sight, but it also provided astronomers with a wealth of important data. Unlike our planet, Mars has 2 satellites, which are very small, irregularly shaped celestial bodies. Observations and spectral analysis suggest that Phobos and Deimos are similar in composition to carbonaceous asteroids, but their exact origins are still a subject of scientific debate. One hypothesis claims that they are the remnants of a small celestial body captured by Mars from the main asteroid belt several billion years ago. The tidal forces of the planet probably tore the object into many fragments, and Phobos and Deimos are the largest of them all. According to another hypothesis, a large protoplanet allegedly collided with young Mars at the dawn of the solar system's formation. As a result of this cataclysm, some of the fragments were thrown into space, where gravitation shaped them into 2 rather large objects. Phobos is the larger of the satellites. It orbits the planet above the equator at an altitude of about 6,000 kilometers, which is about 64 times less than the distance from the Moon to the Earth. Incidentally, some man-made satellites above our Earth drift 3 to 5 times higher than this celestial body. However, Phobos is so modest in size that when observed from the surface of Mars, it appears 3 times smaller than our Moon to us, even at this distance. Another surprising fact is that Phobos has an extremely low average density, approximately 1.9 grams per cubic centimeter. This means that up to 40% of its volume must be hollow. It is possible that this object, like some asteroids in our system, consists of several pieces of debris held together by gravity alone. Due to tidal forces, Phobos is gradually losing height, about 1.8 meters per century. It is estimated that in 10–11 million years, it will be crushed by the pull of Mars into many fragments, and that after another 33 million years, they will finally collapse onto the surface of the red planet. By that time, Mars will be likely to lose its second satellite, Deimos. Currently, this celestial body is moving in a circular orbit with a radius of about 23,500 kilometers, but this distance is gradually increasing. Calculations show that in a few million years, the satellite will finally leave the gravitational influence of Mars and float in space quite independently. Deimos is a very dark object because its surface absorbs almost 93% of the light shed on it. The satellite's small size means that its disk cannot be seen from Mars with the naked eye. Deimos appears to the observer as a pinpoint source of light, even though quite bright. Its orbit makes it appear to drift across the Martian sky towards Phobos, but this is just an illusion. In fact, both satellites orbit Mars in the same direction. Saturn's rings do not have a clear-cut border. The width of their visible part is about as much as 280,000 kilometers, although there are thinnest clusters of dust and rarefied gas beyond these borders. These structures' diameter reaches 16 million kilometers, according to some estimates, although they cannot be seen from the Earth on account of their extremely low density. In spite of the impressive dimensions, the total mass of the ring system is quite small by space standards and is estimated at 3 × 10⁻19 kilograms, which is about 2,000 times lighter than the Moon. Solid objects account for only 3% or so of the structure's overall volume, with the rest filled with rarefied gas and cosmic dust. The disk surrounding Saturn is conventionally divided into several large rings. However, a rather powerful optical telescope will reveal each of them to be clearly made up of a large number of thin circles separated by narrow gaps. These gaps form due to the gravitational influence of both the planet itself and its many satellites. Some of them are as much as several hundred kilometers wide. Even though Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are next to impossible to see, For example, the D ring, the closest to the planet, which consists of tiniest water ice crystals and frozen methane. Its upper border is posited to be located 16,500 kilometers above the planet's conventional surface. As for its inner part, the ring has no clear-cut border and gradually fuses with Saturn's atmosphere. Next to it is the brighter and more massive C ring, which is approximately 17,500 kilometers wide. It is comprised of space objects measuring up to 2 meters and which make up just 0.033% of the disk's overall mass. The brightest and most outstanding part of the disk is located further and is designated the B ring. It begins roughly 34,000 kilometers above the surface of the gas giant, and its width reaches 25,000 kilometers. The thickness of the larger part of the ring does not measure over 5 to 10 meters, while its outer part forms a vertical rim towering up to 2.5 kilometers high. The outermost visible ring of Saturn begins 64,000 kilometers above the planet's surface. It is roughly 14,600 kilometers wide, harboring not only comparatively large ice bits of 10 meters and more, but some satellites as well, such as Pan, Daphnis and others. The existence of such large objects may prove the theory of ring formation following the destruction of the ice satellite. Alternatively, they may have formed at a later time as a result of smaller fragments colliding and merging. Beyond this part of the disk, there lie the almost unobservable F, G and D rings, which formed from cosmic dust and rarefied gas. It goes without saying that most of Saturn's large satellites actively interact with the rings. Traveling as far as 179,000 kilometers away to the region of the so-called E ring, the celestial body dubbed Enceladus is to be found. With a diameter measuring just 500 kilometers, it does not qualify as one of the gas giant's largest satellites, but it stands out for other reasons. The point is that Enceladus is one of the few celestial bodies in our system where there are clear manifestations of cryovolcanic activity. Analysis of the observed emissions proves that there is an ocean of liquid water under its surface. Mathematical modeling shows that its temperature measures from 45 degrees Celsius below zero in the upper layers to 0 degrees at the bottom. Due to a high content of dissolved salts and ammonia, the ocean does not freeze over even in sub-zero temperatures, with the icy shield about 2 kilometers thick covering and thermally insulating it. The celestial body's surface temperature is about 75 Kelvin or 198 degrees Celsius below zero. Its atmosphere is extremely rarefied and is 91% water vapor. Other elements making it up are nitrogen, carbon dioxide and methane. Powerful geysers that erupt from time to time through cracks in the icy crust of the satellite regularly supply its atmosphere with chemical elements, but the celestial body's weak gravity is not enough to prevent the atmosphere from floating away. The upper region of the atmosphere is constantly losing some amount of particles that go to sustain the E-ring. On the other hand, Enceladus constantly captures material from the space around it, thus ensuring its peculiar chemical balance. It is known that geyser activity of this celestial object depends on its orbital movement. It is likely that Saturn's tidal forces deform the satellite's icy shield, causing it to crack in multiple places and to erupt. It is also known that the cryogeyser's emissions contain elaborate organic molecules, which may mean that the conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Also, the gas giant's fifth largest and most massive satellite, Tethys, can be seen approximately 300,000 kilometers away from it. It is peculiar for sharing the same orbit with two other celestial objects, Telesto and Calypso. They are located at the so-called stable Lagrange points, with Telesto 60 degrees ahead of the main satellite in its movement along the orbit, while Calypso, on the contrary, lags 60 degrees behind. Unlike the massive spherical Tethys, these celestial bodies are not that large and are irregular in shape. They measure roughly 20 to 30 kilometers in diameter, with their overall mass just several trillion tons, which is modest by space standards. Interestingly, modeling shows that Calypso and Telesto could not have originally formed in the same orbit with a more massive body following it, which means that they arrived to join it at a much later time. As for Tethys, it is a celestial object with a diameter measuring about 1060 kilometers, made up of mostly water ice, with some rocky impurities in its composition. The most outstanding feature of its relief is the giant impact crater Odysseus. Its diameter measures around 450 kilometers, which is about twice as small as the diameter of Tethys itself. Its depth reaches as far down as 3 kilometers. There is also an easily noticeable chasm of enormous proportions on the satellite's surface, which is called the Ithaca Chasma. It is as long as about 2,000 kilometers. That is about a third of the celestial body's circumference, and as much as 100 kilometers wide. As for its depth, it ranges from 3,000 to 5,000 meters, and the bottom is pockmarked with a great number of craters and minor irregularities of the surface. According to one of the theories about it, the Ithaca chasm formed as a result of Tethys's subsurface ocean freezing over. On turning into ice, the water expanded in size and erupted through the satellite's outer crust. Another assumption about the chasm has to do with the Odysseus crater. It is thought that the impact waves traveled across the entire surface of the satellite and caused a powerful resonance around its circumference. As a result, Tethys's crust cracked, forming this incredibly large chasm. Titan is located about 10 astronomical units from the Sun and is outside the habitable zone of our star. It is Saturn's largest satellite, and its orbit lies well outside the Great Rings, at a distance of about 1,200,000 kilometers from the center of the planet. The trajectory of the celestial body is close to circular, and a complete orbit around the gas giant takes a little less than 16 Earth days. Titan's diameter is 5,152 kilometers, which is 5.6% larger than that of Mercury. At the same time, the mass of the celestial body is relatively small at only 1.35 times 10 to the power of 23 kilograms, which is about 40% of Mercury's. Calculations show that the satellite's average density is about 3 times less than that of the Earth, which means it has a completely different chemical composition. According to contemporary concepts, Titan has a massive core at its center, about 3,400 kilometers in diameter and made up of various silicon compounds. It is surrounded by a thick layer of densely packed ice, which is at the bottom of a cold liquid ocean hundreds of kilometers deep. The ocean, in its turn, contains large amounts of dissolved ammonia, methane and various caustic salts, so that its freezing point is markedly lower than that of ordinary water. For this reason, Titan's subsurface ocean remains liquid even in sub-zero temperatures. It is bound by a thick crust around 100 kilometers thick, consisting of a mixture of water ice and methane hydrate. The tidal forces of the nearby Saturn are continuously deforming it, causing massive rifts and fractures. This causes large cryovolcanoes to form, ejecting great quantities of methane, ammonia and water onto the surface of the celestial body. Methane plays about the same role in Titan's atmosphere as water vapor on Earth. The fact is that the average surface temperature of the satellite is only about 94 Kelvin or 179 degrees Celsius below zero, which is slightly below its boiling point. Natural variations in this parameter cause hydrocarbon vapors to condense and precipitate, forming methane seas, lakes and rivers. Titan's atmosphere is composed mainly of hydrogen, which makes up about 98.4% of its volume, while methane accounts for about 1.6%. Due to its extremely low temperature, the satellite's atmosphere remains condensed near its surface, and the ring of the mountains surrounding it is less than 500 meters high. Most of the surface of the celestial body is permanently obscured from our eyes by multi-layered clouds and an orange-yellow tholin haze. This unique weather phenomenon is a fog formed by tiny droplets of liquid methane and dissolved organic matter, which gives Titan its characteristic hue. This haze pervades Titan's surface, absorbing and scattering visible light but transmitting infrared light. This peculiarity leads to an unusual anti-greenhouse effect, which cools the satellite's surface by roughly another 10 degrees. This effect makes Titan difficult to explore, but thanks to the Cassini's orbiter's infrared cameras, Titan was in parts mapped out earlier this century. Of course, it is not as accurate as we would prefer, but even this much is enough to outline the most striking features of the celestial body's surface. The face of Saturn's largest moon is full of contrasting spots. Some of these reflect most of the light that falls on them, while others are relatively dark in color. One such area is slightly south of the equator and is called Aztlan. One of Titan's highest mountains, Mount Doom or Doom Mons, is located here, towering about 1.5 kilometers above the surrounding plains. The whole mountain reaches up to 60 kilometers in diameter. Its summits are craters, and its slopes have relatively fresh traces of turbulent flows. This may suggest that Doom Mons is an active cryovolcano. To the northeast from it is Titan's deepest depression, called Sotra Patra. It is a giant depression about 30 kilometers long, the bottom of which is located about 2 kilometers below the adjacent plains. It is thought to be the mouth of a huge cryovolcano, and is part of a single tectonic structure along with Doom Mons located close by. To the north of Doom Mons, there stretches the immense Mahini Fluctus, a vast area covered by Doom Mons' ejections. The area extends for about 180 kilometers and varies in width from 15 kilometers in the south to 60 kilometers in the north, where torrents of frozen material alternate with expansive fields of sand dunes consisting of a mixture of frozen methane and water ice. Our flight will continue over the dark area of Fensel. The largest impact crater of the celestial body, Minerva, is located in its northwestern part. It reaches 440 kilometers in diameter, which is about 3 times larger than any other crater on Titan. The depression is about 200 meters deep, and the ring of the mountains surrounding it is less than 500 meters high. The fact is that according to studies, Minerva is not only the largest, but also the oldest extant crater on Titan. Different estimates put the age of the crater at between 300 million and 1.2 billion years. Erosion and tectonic processes have severely damaged the crater, and it is only thanks to its sheer size that it is still visible. Minerva has a well-defined internal structure. At its center there is a small flat plain, surrounded by a ring of hills. This region, with a total diameter of about 200 kilometers, is rather light and clearly visible from space. It is surrounded by a so-called moat, a stretch of dark plains about 50 kilometers wide. This is followed by a ring of low mountains that form the outer boundary of the crater. Our flight next takes us to the south. Here is one of Titan's most impressive and mysterious landmarks, Hautei Arcus. This is a unique formation in the solar system and is a bright arc-shaped region about 600 kilometers long. Radar data from Cassini shows that Hautei Arcus is a natural boundary between the Rocky Mountains in the northeast and a wide valley in the northwest. It is also noteworthy that some parts of this area change color from time to time. This phenomenon is thought to be linked to the eruptions of cryovolcanoes, whose emissions cover the surface of the satellite in a thin layer and then flow into a nearby valley or evaporate into the atmosphere. From space, one can clearly see light channels similar to riverbeds running from the mountains of the Haute Regio to the northwest. This is where Xanadu is located, which is a vast lowland area with highly rugged terrain. Its northwest boundary is formed by Mithrim Montes, which are 3 parallel ridges stretching for about 150 kilometers, with an average height of 1.9 kilometers. Among the peaks of the southern range is the highest peak on Titan, reaching 3,337 meters. Standing on top of it and looking west, you can see a vast dark plain stretching several hundred kilometers in front of you. It is called Shangri-La, and it is thought that this whole area used to be flooded with liquid methane. It is assumed that it may have persisted beneath the topsoil, similar to the Earth's underground water. Most of this region is below average elevation and has a comparatively flat terrain, but lighter hills can be seen in some places. In the past, these may have been islands in the middle of a hydrocarbon sea. To the west of Shangri-La is the bright Adiri upland area, clearly visible against dark regions around it. The area extends for up to 2,500 kilometers and is a veritable network of numerous drainage canals and caves clearly visible in the photographs. These are thought to have been formed by abundant flows of liquid hydrocarbons. To the west of Adiri is the vast dark lowland area of Belette, and to the east, near the border with Shangri-La, is the Huygens landing site, so far the only vehicle that got to touch down on the surface of an object in the outer solar system. The descent probe was part of a science program called Cassini-Huygens. Together with the Cassini automatic probe, it left Earth in 1997 to spend 7 years in interplanetary space. The spacecraft entered the orbit of Saturn only in 2004, and in early 2005, Huygens reached Titan and plunged into its atmosphere towards new discoveries. Cassini, on the other hand, remained in orbit around the gas giant to carry out its part of the research program, as well as to continue serving as a transponder for the lander. The probe spent just under 2.5 hours in the atmosphere, gradually dropping speed using a sophisticated parachute system. Eventually, by the time it touched down on the surface, its speed was 4.4 meters per second. The probe successfully withstood a momentary 15-fold overload and soon went on to collect information. Huygens was equipped with a vast array of scientific instruments, most of which were designed to study different aspects of the satellite's atmosphere. The probe used them to measure the strength and direction of air currents, as well as the electrical conductivity, temperature and composition of the atmosphere. The probe also took photographs and made audio recordings, and on landing, it examined the composition and properties of the ground. The first thing the cameras saw after making contact with the surface was a flat plain, dotted with rounded rocks of various sizes, the shape of which clearly indicated the impact of powerful fluid currents. A special drill was also used to sample the surface, penetrating 15 centimeters into the ground, while multiple sensors measured its density, texture and composition. It turned out that a thin layer of small rounded pebbles lay on a relatively soft but dense substrate, similar in consistency to wet sand or dense snow. Also, methane gas was released during the drilling process. The ground at the Huygens landing site is believed to have been like sea sand, saturated with liquid hydrocarbons. In total, the probe transmitted around 500 megabytes of information to Earth, including 350 photographs. Further careful analysis revealed several unique features of the celestial body related to its atmosphere. For example, it turned out that at an altitude of about 80 kilometers there is a layer of almost complete calm, as if separating Titan's atmosphere into 2 parts. Neither air currents of the upper atmosphere nor winds of the surface reach this layer. What caused this phenomenon is not yet known. Another feature is that Titan has two ionospheres. The first of these is located at an altitude of about 1,200 kilometers. It is a layer of heightened electrical conductivity with a large concentration of ionized particles. This layer is known to be formed by stellar wind streams and cosmic radiation. The second ionosphere lies much lower, at an altitude of about 60 kilometers, and the reason for its formation is still debatable. Moving northwest from the Adiri area, we reach Titan's largest hydrocarbon reservoir, the Kraken Mare. Its total area reaches 400,000 square kilometers, which is slightly smaller than the Black Sea. Due to the high viscosity of the liquid hydrocarbon mixture, it has not yet been possible to measure the exact depth of the reservoir. It is only known that in most of the area, it is over 200 meters. Another large natural basin, the Ligeia Mare, is located slightly to the north, near Titan's pole. Its diameter reaches 500 kilometers, and its area is about 100,000 square kilometers, which is about 3 times larger than Lake Baikal. The seas are connected to each other by the narrow and long Treves Fretum, 173 kilometers long. Also in the subpolar region, there are many smaller lakes and lagoons filled with liquid methane. In 2014, analysis of earlier images beamed back by Cassini revealed a large bright object on the surface of the Ligeia Mare. On comparing photographs taken at different times, it was established that within a few months the mysterious object had grown to 260 kilometers in diameter, to disappear almost instantly without a trace. Several hypotheses have been put forward to explain it. According to one of them, temperature differences lead to a constant stirring of layers of liquid hydrocarbon mixture in the Ligeia Mare. This causes nitrogen bubbles to form and rise to the surface from the depths of the reservoir, and thus form large clusters of persistent shiny foam. Due to the high viscosity of the hydrocarbons, such bubbles can reach 4.5 centimeters in diameter and remain stable for months. From space, these structures resemble large islands because they reflect infrared radiation well. Such bubbles would have been a significant hindrance to the operation of a submersible probe, which was scheduled to be launched to Titan back in 2010. However, the mission was postponed indefinitely for various reasons. A higher priority was given to the Dragonfly program, which NASA is working on now. The vehicle is currently in the design phase and has just recently passed key tests of its blades. The launch from Earth is scheduled for 2027. As conceived by its creators, Dragonfly will be an octocopter, an aircraft with 4 twin propellers. This design will allow it to stay in the air even if it loses several blades, unlike its predecessor, the Ingenuity Mars helicopter. A radioisotope thermogenerator, powerful enough to enable the vehicle to climb to a height of 4 kilometers and travel at a speed of about 36 kilometers per hour, will be used as the power source. The scientific capabilities of the probe are also impressive. It will be equipped with a versatile camera capable of producing both panoramic photographs of the surrounding terrain and macro images of the ground. At the same time, the mass spectrometer will make it possible to determine the chemical composition of atmospheric samples and the internal structure of rocks. Perhaps Dragonfly's data will help us clarify an important question. Do we at least have a chance of encountering primitive life? The possibility of life on Titan remains hotly debated. On the one hand, the extremely low surface temperature, the presence of extremely toxic hydrocyanic acid in the atmosphere, and the absence of liquid water would likely rule out the presence of biological life as we know it. Titan's atmosphere, on the other hand, exhibits an incredible diversity of organic compounds. Nitrogenous bases and amino acids, which are the building blocks of proteins, RNA and DNA, could be naturally synthesized on its surface. It is also known that liquid methane can serve as a solvent and potentially play the role of water in biochemical reactions. In addition, experiments show that under certain conditions, a mixture of liquid hydrocarbons with phosphine forms an environment similar to the primordial soup of the early Earth. This means there's a chance of encountering downright exotic forms of life on the surface of the satellite. More than 4 centuries ago, back in 1610, Galileo Galilei made one of the greatest astronomical discoveries of his time. Through his telescope, quite small by modern standards, he managed to make out 4 objects close to Jupiter. One of them was named Ganymede and is now considered the largest satellite in the solar system. The other 2, Europa and Callisto, have proven to be promising candidates for the search for extraterrestrial life. The 4th satellite, located closest to the gas giant, was dubbed Io. For a long time, technical limitations have prevented us from seeing details of the surface of this celestial body, and its composition and internal structure remained a matter of conjecture. However, thanks to the advancement of science, astronomers have gained more and more information over time. Today, Io is known to be one of the largest satellites in the entire solar system, second only to Ganymede, Titan and Callisto in size. Its radius is 1,821 kilometers, and its mass reaches about 8.9 times 10 to the power of 22 kilograms. If we compare this celestial body with the Moon, it turns out that these objects are almost identical in size. However, if we compare the masses, we will notice that Io is more massive than the main satellite of our planet by as much as 21%. This suggests that the average density of this space object is higher than that of any other satellite in the solar system. According to calculations, it is about 3.5 grams per cubic centimeter, which is noticeably higher than most non-metallic rocks. And to understand the reasons for the anomalous density of Io, we need to look deep into it. According to today's concepts about the structure of celestial bodies, Io has a relatively compact core at its center, made up of iron and sulfur. It accounts for about 20% of the satellite's mass, and its radius, according to different estimates, is between 350 and 900 kilometers. Calculations show that given such parameters, internal heat release will be insufficient to melt most of the core. This is also confirmed by the fact that this celestial body has almost no magnetic field of its own. Mathematical modeling shows that the satellite's core is surrounded by a solid mantle, at least 75% of which is made up of the magnesium-bearing mineral forsterite. According to calculations, its outer part is molten and forms an ocean of magma about 50 kilometers deep. Its temperature is about 1600 Kelvin, which is more than 1300 degrees Celsius. Deeper layers are under high pressure, and therefore they retain a solid state even at extremely high temperatures. In its turn, the mantle is covered by the lithosphere, which is between 12 and 40 kilometers thick. Despite its considerable thickness, it is not monolithic. In some areas, the surface of the celestial body is cracked, forming large structures filled with lava. At the same time, spectral analysis shows that unlike with most satellites, there is virtually no water, ice or frozen gases on Io. The outer surface of the celestial body consists of basalt and sulfur for the most part, but also has flecks of other dense minerals. And this is exactly what accounts for its abnormally high density. By the early 21st century, Io's surface had been explored by at least 5 automated orbital stations, but it's the Pioneer and Voyager programs that provided the most key insights back in the 1970s. In the images transmitted by the probes back to Earth, scientists detected giant gas emissions, some of them reaching as high up as 500 kilometers. This observation opened a new page for scientists in the study of the solar system, because previously active volcanoes were known to exist only on Earth. For the first time, it was not frozen lava flows that had been frozen for a while, or volcanoes that went extinct billions of years ago that astronomers saw outside their home planet. They saw active eruptions, in some respects even more impressive than those on Earth. In total, about 400 active volcanoes have been found on the surface of the satellite, which is about 2.5 times fewer than on our planet. However, its area is significantly more modest than that of the Earth, which allows us to consider Io the most active volcanic object in the solar system. It is not surprising that such an unusual celestial body has attracted close attention of astronomers. During the exploration missions, a huge number of photographs of different resolutions were accumulated, thanks to which it was possible to compile a complete geological map of Io in 2012. Its quality allows us to see the largest features of the celestial body's relief, such as plains, mountain ranges, lava flows, and of course, numerous volcanoes. And one of the most notable features is certainly the huge orange-brown ring located in the southeastern part of the satellite. This vast area extends for more than 1,000 kilometers and is comparable to a large African country in terms of its size. It is believed to be formed by deposition of sulfurous emissions from the ancient Pele volcano, which is located in the center of the ring. Analysis of photographs, taken both in the infrared and visible ranges, shows that in the center of the ring there is the patra of this volcano, which is a multi-level cavity reaching 30 by 20 kilometers, filled with lava. Incidentally, the temperature of the molten rock surface is distributed unevenly and constantly varies, reaching 1300 degrees Celsius at the hottest points. The patra is believed to be connected to the satellite's glowing mantle by an underground channel. The lava inside the rift is constantly stirring due to the fact that volatile substances dissolved in it try to rise upwards with a flow of molten rock following. Because of this, the thin crust of solidified matter covering the surface of the lake occasionally cracks and breaks, causing outbursts and lava ejections. Some of them can be upwards of 300 kilometers in height, sending solidified sulfur and rock particles straight into space. Gradually losing speed under the influence of gravity, the volcanic precipitation disperses over the surface of the satellite and then gently descends downwards. This is how the giant ring is formed, so clearly visible from space. Many of Io's volcanoes have similar formations, but the Pele ring is the largest. It is active volcanism that is the main reason for the formation of Io's special, unique atmosphere. According to available data, the atmosphere of the satellite is very thin and mainly consists of sulfur dioxide. At the same time, its density varies greatly from region to region. For example, in volcanic plumes, the gas pressure is 25 million times lower than on Earth. Away from eruptions, meanwhile, the atmospheric pressure on the day side of the celestial body is on average 1 billion times lower than the value we're accustomed to, and the night hemisphere of the satellite is almost in complete vacuum. The atmospheric density there is trillions of times lower than the Earth's. Also, despite the fact that Io's atmosphere is extremely rarefied, and the satellite has no magnetic field of its own, polar lights have been observed on Io, charged cosmic particles, accelerating in Jupiter's magnetosphere, bombard the nearby satellite, causing a multicolored glow in its atmosphere. Interestingly, Io's auroras, unlike those on Earth, most often occur at the equator, as it is there that the particles flying along a tangential trajectory have to penetrate the thickest layer of the atmosphere. Meanwhile, our journey across the expanses of Io will continue in a northwestern direction. After crossing the boundaries of the Pele sedimentary ring, we will soon see the vast range Boisoli Montes. Its total diameter is about 540 kilometers, and among other peaks, the giant peak called South Boisoli Mons stands out. Measuring 145 by 159 kilometers at its base, this mountain rises more than 18 kilometers above the average level of the satellite, twice as high as the Earth's Mount Everest. The total area of the entire elevation is almost 18,000 square kilometers, which is comparable to the size of a small European country, such as Montenegro or Slovenia. The appearance and structure of this relief feature suggest that it appeared as a result of a tremendous tectonic cataclysm. Probably in the distant past, a fragment of the satellite's forming lithosphere tilted and partially sank into the mantle, while one of its edges remained forever elevated above the surface. As a result, the southeastern slope of the mountain is a steep precipice, about 15 kilometers high, making it one of the highest ledges in the entire solar system. Such formations are impossible on Earth due to higher gravity, and on other planets and satellites due to low tectonic activity. For this reason, South Boisoli Montes can be considered a truly unique peak in the solar system. Moving on in a northwesterly direction, we will soon reach a gigantic chasm called Loki Patra. This formation is the largest volcanic depression on Io, with a diameter measuring roughly 250 kilometers. Thus, the total area of this great chasm exceeds 50,000 square kilometers, which is about 1.5 times larger than that of Lake Baikal, one of the most majestic lakes on our planet. However, unlike terrestrial bodies of water, this chasm is filled with hot sulfur silicate lava. Several dozens of kilometers down from the surface, this lava lake communicates directly with the mantle, which serves as an inexhaustible source of molten matter for it. In the calm state, the temperature of the Patra's surface varies from 270 to 313 Kelvin, which corresponds to the range from 3 degrees below zero to 57 degrees Celsius above zero. Such a low value is due to the fact that the upper lava layers are cooled by contact with Io's rarefied atmosphere. As a consequence, they gradually solidify, forming a slowly growing hard crust, the mass of which reaches a critical value within 400 to 600 days. It then cracks under its own weight and sinks, causing waves of flooding that slam into the surface of the lake at a rate of about 1 kilometer per day. Gradually, the lava lake calms down and begins to be covered with a slowly solidifying solid layer again, until the next flooding cycle. Since water and carbon dioxide, crucial for supporting life as we know it, are practically non-existent on the surface of Io, this celestial body is considered unfavorable for biogenesis. However, the conditions on the surface of Loki Patra and other lava lakes, hypothetically, may be suitable for the origin of unusual life, resistant to high temperatures and obtaining energy from chemical reactions involving sulfur or iron. There are such creatures on Earth as well, that mostly live in the vents of underwater volcanoes or isolated oceanic caves. Still, due to Io's tectonic activity and extreme temperature variations on its surface, realistically, the probability of this phenomenon is rather low. Interestingly, it may be observed that although the uplands and volcanoes are the most remarkable features of Io's relief, they occupy a relatively small area. Tectonically active areas of the surface are separated by vast and relatively flat regions covered by a thick layer of sulfurous sediments. When viewed from space, these areas stand out with lighter colors, and the largest of them extend for thousands of kilometers. For example, if we head west from the Petra Loci, passing numerous small volcanoes and lava flows, we will soon reach an area called Media Regio. It is a bright and relatively smooth, irregularly shaped area surrounded by mountains and large paterae. Its diameter is variously estimated to be about 2,600 kilometers, and its area accounts for about 12.6% of the satellite's total surface. While most of this region is uniform and smooth, in some places the plane is cut by lava flows associated with adjacent volcanoes. It is assumed that the lithosphere beneath Media Regio has an exceptional thickness, forming something reminiscent of the Earth's continents. That is the reason why such a large surface area has retained its integrity for a very long time. According to another hypothesis, the upper layers of the satellite's mantle are melted in fragments, and there is no liquid magma beneath the tectonically inactive plains. Observations show that in contrast to the volcanic regions, the plains of Io are characterized by a cold climate. Thus, the temperature of Media Regio differs slightly from the average of the entire satellite and is only 110 Kelvin or 163 degrees Celsius below zero. That is hundreds of degrees colder than in most of the volcanic paterae. At this temperature, sulfur dioxide with atmospheric emissions settles as frost on the satellite's surface, forming a flat and smooth relief, colored in hundreds of shades of yellow, red, and black. Whatever is the case, future research will surely yield much more data about this region. Having covered the smooth relief of the sulfurous hills of Media towards northwest, we will see another large chasm, known as Almirani. Just like most of the satellite's volcanoes, it is a lava-filled drift in the crust of the celestial body. Its diameter at its widest point reaches only 37 kilometers, but when viewed from space, this volcano is almost as prominent as the largest features of relief on Io's surface. The reason why it produces such an impression is that Almirani is surrounded by several giant flows of solidified lava. With their dark color against the background of the light-colored plains around, they produce a stark contrast with their brightness. The largest of these flows extends northwards for more than 300 kilometers and is up to 60 kilometers wide. Thus, this feature is the largest active lava flow in the solar system. The second largest lava flow extends westwards for as much as about 250 kilometers. Previously, it was considered an independent formation, but more detailed images of the surface showed that this object is also part of Almirani. In addition, to the east of the main Petra, there is a crown of small dark streams, the color of which suggests that they consist of silicates, which first melted and later solidified. Almirani has a complex internal structure. It is assumed that in addition to the main active area, there are magma tubes lying beneath the surface of the satellite in this region. Their occasional outbursts are the cause of eruptions outside the main rift. Observations in the infrared spectrum show that the main Petra is heated to about 1900 Kelvin or 1630 degrees Celsius, and the temperature of individual hot spots surrounding it reaches 1200 Kelvin or 930 degrees Celsius. It is likely that this value is so high due to the fact that directly beneath the volcano there is an upward magma flow, carrying molten matter from the lower mantle layers. There is also evidence suggesting that Almirani is likely a very young shield volcano. Over time, the lava it spews out will form a vast flat shield, hundreds of kilometers in diameter, and it is likely that this volcano will become similar to Olympus Mons on Mars. It is hardly disputable that in spite of its relatively small size, Io exhibits highly anomalous tectonic activity. In fact, because of its low mass, it does not have sufficient reserves of radioactive substances, the decay of which is the source of internal heat for most planets. It is believed that the reason for the abnormal activity of this celestial body is the tidal interaction with Jupiter. Combined with the orbital resonance that keeps Io in a stable orbit, the gas giant's attraction strongly heats up the satellite's interior and deforms its crust, and this causes frequent and powerful eruptions. Combined with low gravity, they become truly spectacular. Giant emissions reach outer space, forming a scattered cloud of particles around the celestial body. Some of them fall back to Io, others are dispersed by Jupiter's magnetic field, bombarding its atmosphere, while others yet settle on other satellites of the gas giant or become part of its rings. And it is these massive emissions that are constantly occurring in a region called Tvashtar Pattery, which is located in the northern part of Io. This region is an area of pronounced volcanic activity with a diameter of about 300 kilometers. This region is reported to contain several volcanic pattery, presumably associated with a single underground lava source. Over the past 3 decades, several powerful and prolonged eruptions have been recorded here. For example, in the years 1999-2000, the height of the eruption reached 385 kilometers, and volcanic fallout covered a surface area with a radius of more than 700 kilometers. In addition, during this eruption, a gigantic amount of sulfur silicate lava spurted out of the Patra and flooded a huge area around. A few years later, in 2006, another large eruption began in the same area, which lasted 530 days, thus becoming the longest cataclysm in the history of observations of Io. This time, the column of emissions rose to 330 kilometers, sending thousands of tons of matter into outer space. Clearly, Tvashtar is a very active region in terms of tectonics, and the study of its emissions will provide a wealth of data on the internal composition and structure of this satellite. It is no exaggeration to say that Io is a unique and very interesting celestial body, still actively studied. In particular, on the 3rd of February 2024, the orbital station Juno flew at an altitude of 1,500 kilometers above the surface of the satellite and beamed back to Earth a lot of high-quality photos. They showed giant chasms in the crust of the celestial body, as well as volcanic plumes and lava flows. It is assumed that in the future, such flights will help to carry out spectral analysis of Io's atmosphere to clarify its composition and parameters. Nevertheless, despite astronomers' interest in this celestial body, no specialized mission is currently scheduled to explore it. The JUICE and Europa Clipper projects focus on Ganymede, Europa and Callisto because of their potential habitability, although NASA specialists did announce working on a mission called IVO at the beginning of the century, which was supposed to focus on Io's volcanoes. It was never realized, for a number of reasons. Pluto is about 40 astronomical units away from the Sun and is a dark and indistinguishable object. This distant celestial body follows a rather elongated orbit around the center of the solar system, completing it every 248 Earth years. We know that Pluto's radius is 1,188 kilometers, which means that it is noticeably inferior in size not only to all the planets of the solar system, but also to some of their satellites, including the Moon. At the same time, observations of the celestial body's proper motion made it possible to calculate its mass with a high degree of accuracy. It turned out to be small, only 1.3 times 10 to the power of 22 kilograms, or 18% of the lunar mass. It is easy to see that Pluto is much more similar to small celestial bodies such as Eris, Ceres or Sedna in terms of its characteristics. This is the reason why it topped the list of dwarf planets in 2006. Due to its long and elongated trajectory, Pluto has a long orbital cycle. Only in 1989 did the planetoid first pass its orbit perihelion since its discovery, approaching the Sun as close as 29.7 astronomical units. Since then, this distance has been continuously increasing and will reach its greatest value in the year 2113. By that time, the dwarf planet will be near its aphelion, which is 49.3 astronomical units away from the center of our system. Thus, Pluto is a very distant and dim space object. That is the reason why it cannot be seen from Earth with the naked eye. And even in images from the Hubble Space Telescope, the dwarf planet looks like a murky brown disk without any surface details. Of course, in such conditions, it is almost impossible to study the celestial body properly. To solve this problem, the New Horizons Unmanned Orbital Station was sent to Pluto in 2006. It took a long 9.5 years to reach its destination. On its way, it beamed back to us detailed images of Jupiter. It wasn't until 2015 that the spacecraft finally reached the main object of its mission. As it flew past Pluto, the station made about 400 observations, collecting more than 6 gigabytes of information, and it took more than a year to transmit this large amount of data to Earth. Unfortunately, the probe's trajectory did not allow photographing the entire surface of the dwarf planet. The fact is that New Horizons did not enter into an orbit around Pluto, but circled round Pluto in order to be able to explore other space objects. Before moving on to the celestial body's terrain features, we need to understand its internal structure. According to the currently accepted model, Pluto has a massive core with a diameter of about 1,700 kilometers, consisting of a mixture of various forms of water ice and rocks in its center. It is surrounded by a 300-kilometer ice mantle. There are probably tectonic processes running in the mantle, and in the moment they are quite understudied. The mantle, in its turn, is covered by a crust, which is a mixture of crystallized gases such as nitrogen, methane and carbon monoxide. According to some assumptions, Pluto's core may generate enough heat to melt some of the icy mantle. In this case, deep beneath the surface of the planetoid, there should hide a very salty and toxic ocean containing large amounts of dissolved ammonia. As for the surface temperature of the dwarf planet, it is very low and is not over 60 Kelvin or 213 degrees Celsius below zero. Our journey around Pluto will start at the most outstanding and well-studied feature of its relief, Tombaugh Regio. This vast area is located in the equatorial zone of the planetoid and is shaped like a heart sketch. This resemblance earned the region its informal nickname, the Heart. Its size reaches 2,300 kilometers, which means that the plane occupies about a quarter of the celestial body's entire area. Tombaugh Regio's surface is not homogeneous. Thus, there is a smooth and light plain in its western part, known as Sputnik Planitia, whose diameter measures 1,492 kilometers. An elevation map will reveal this region to be a vast lowland area. It is covered with a thick layer of nitrogen ice, as well as carbon monoxide and solid methane. These substances have a light coloring, which makes some parts of the plane reflect up to 90% of the light falling on them. There are also virtually no craters, which means that the region is very young in geological terms. According to the main hypothesis, Sputnik Planitia formed about 100 million years ago, when Pluto experienced a collision with a large celestial body. As a result, a huge impact crater appeared. It was filled with contents of the hypothetical inner ocean of the dwarf planet, which rapidly froze there. Some typical features of the relief of the plane can serve as evidence of this. For example, there are quite a number of smooth surface areas on it, ranging from 20 to 30 kilometers in size, with hills and depressions concentrated on the borders between them. This kind of structure resembles convection cells, which appear in any fluid heated from below. This may serve as an indirect confirmation of the hypothesis of Pluto's warm interior. Tombau Regio is surrounded by comparatively high mountain ridges. Thus, Hillary Montes, lying to the west from Sputnik Planitia, reach 3.5 kilometers in height. Tenzing Montes are located in the southern part of the heart. Some of them tower as high as over 6 kilometers above the dwarf planet's average surface level, which makes this ridge the tallest one found on Pluto. Remarkably, these rocks are likely to be made up mostly of water ice. And in temperatures as low as here on Pluto, water ice is as solid as rock. Moving a little further south, we can see a deep basin surrounded by massive multi-layered ridges of ice and rock. It is assumed that it may be the vent of an ancient cryovolcano, and the rock around it is its numerous frozen eruptions. Their chemical composition is of great interest to science, because once it is known, the peculiarities of Pluto's inner makeup may be studied. The eastern part of Tombau Regio is darker. In addition, its surface is pockmarked with a great number of craters, which means that this region is by far older than Sputnik Planitia. Moving further east along the equator, we will see a chain of dark spots, hundreds of kilometers in diameter. These objects are called maculas and are named after dark deities of various cultures. For example, one of them is named Balrog. Together they form a giant structure called the brass knuckles, encompassing the celestial body along the equator. The maculas are separated by high mountain ranges, and their surface is cut by deep crevices reaching hundreds of kilometers in length. Cthulhu Macula stretches to the west from Tombau Regio. It is the largest dark spot on Pluto, measuring almost 3,000 kilometers. Its surface reflects not more than 30% of the light shed on it, which is a stark contrast with the bright and light Sputnik Planitia close by. There is still no reliable information about what maculas are. It is assumed that their dark color is due to a high content of tholins, combined with a relatively large concentration of impact craters. This indicates that maculas are remarkably old. It is also known that the surface of Cthulhu Macula is heterogeneous. Thus, its relief in the western part is undulating. The central part is a smooth plain, and the eastern part is covered with mountains and craters. Leaving the grim spot of Cthulhu Macula behind us, let's head north. Here lies Lowell Regio, the vast valley surrounding Pluto's North Pole. Surprisingly, it is this place that is currently the most illuminated part of the celestial body's surface. The point is that Pluto's axis of rotation has a very large tilt with respect to the plane of its orbit, so in its movement it found itself facing the Sun with its North Pole. It is assumed that it's for this reason that the density of Pluto's atmosphere has tripled over the past 30 years, despite the growing distance from the Sun. It is likely that the Sun's rays evaporate nitrogen ice settled at the pole, which goes into the dwarf planet's atmosphere. In its orbital motion, Pluto has a number of peculiarities compared to the planets of the solar system. In addition to the fact that its orbit has a noticeable tilt to the ecliptic plane, the planetoid itself constantly performs cyclic oscillations near a certain point. This is due to the presence of a large satellite, gravitationally affecting the dwarf planet. It is called Charon, and its mass is 1.52 times 10 to the power of 21 kilograms, which is more than 11% the mass of Pluto itself. As a consequence, both celestial bodies orbit a common mass center between them. They are tidally locked to each other, so they face each other with the same sides at all times. Unlike Pluto's, the surface of its satellite is noticeably darker and shows an abundance of water ice, which is mixed with methane and nitrogen only in some regions. In addition to Charon, there are several other satellites, but all of them are much smaller and are irregular in shape. Nix and Hydra, discovered in 2005, measure several tens of kilometers, and Kerberos and Styx, which were discovered later, are not over 16 kilometers in diameter. All of these celestial bodies consist mainly of water ice and were probably captured by Pluto's gravity from the Kuiper Belt. Unfortunately, a significant part of Charon was not caught in the field of view of the New Horizons probe's cameras, but many curious terrain features can be found on the visible surface of the celestial body. For example, to the south of the equator, there lies a vast region called Vulcan Planum. Its area is not known precisely, but it is not less than 400,000 square kilometers, which is comparable with the size of an average European country. Here, the highest summit of Charon can be found, Kubrick Mons. Its diameter measures around 40 kilometers, and according to some estimates, its height reaches 4,000 meters. In addition, the mountain is surrounded by a wide circular moat, as it were, up to 2 kilometers deep. According to some assumptions, Kubrick Mons may in fact be a cryovolcano. In this case, it is very likely that the area around it has sunk under its own weight due to the emptying of the underground reservoir. To the north stretches the vast Oz Terra, the surface of which is pockmarked with many craters. It is separated from Vulcan Planum by a system of giant ledges and crevices with a total height of about a kilometer. The largest of them is Serenity Chasma, which is 200 kilometers long with a width varying from 40 to 50 kilometers. It can be as deep as 7 kilometers, and it is difficult to explore its bottom because of the thick shadows cast by the steep slopes. Further north yet, near the very pole, there is the giant Mordor macula. Its diameter reaches 475 kilometers, and its origin is still debatable. According to the dominant hypothesis today, nitrogen and methane floating from Pluto's atmosphere were trapped by Charon's gravity and so settled at its poles. After exposure to ultraviolet radiation, they turned into tholins and gradually concentrated in the ice of the celestial body. This assumption needs verification, which will be an object of future missions. Charon largely remains a mystery to us because its research is only just starting. Although the Pluto-Charon system is undoubtedly one of the most interesting structures in the solar system, it is still understudied. Unfortunately, the New Horizons probe left its environs long ago, and the celestial bodies themselves are rapidly moving away from us, taking their secrets along. At the moment, the probe is more than 50 astronomical units away from the Earth, and from time to time beams back to us some extremely important data. By about 2030, all of its systems will eventually fail, and the probe will be left all alone in the chilling recesses of space. On the 15th of April 2021, the automatic space probe New Horizons became the 5th spacecraft in the history of the humanity to go beyond the point of 50 astronomical units from the Sun. It was the Voyagers that had crossed this mark before, with the probes Pioneer 10 and Pioneer 11 the first ever to do so. None of these space wanderers are likely to ever return to the Earth. With some of them still active on their missions, others have gone quiet forever. Spacecraft New Horizons. Start of mission 19th of January 2006. Distance to Earth 52 astronomical units. Speed 14 km per second or 3 astronomical units per year. Main goal Pluto and Charon. Mission status successfully completed. Condition operational. Just like most other interplanetary space probes, New Horizons performed a gravity assist maneuver near Jupiter before setting out to its target. Not only did it greatly boost the spacecraft's speed, but also allowed it to capture high-quality images of the largest planet in the solar system alongside its satellites. Besides, the probe's cameras captured the first video ever of an erupting volcano on the surface of Jupiter's satellite Io. After the gravity boost had been completed, the probe made for the main target, Pluto. The spacecraft reached the planetoid's environs in January 2015. The mission's main goal was to explore Pluto and Charon from different perspectives that involved taking photos of and mapping these remote space object surfaces. In addition, the probe estimated the magnetic field's values and the solar wind activity close to the objects and collected information about their atmospheres and surface reflection properties. It goes without saying that the program also involved search for Pluto's as yet undetected satellites and more accurate measurements of Pluto's orbit's parameters. Having completed the main mission, the probe continued to be useful. It flew beyond Pluto's orbit and went on to explore objects in the Kuiper Belt. That is how images of Quaoar, R1 and Arrokoth were produced. Thanks to the probe's cameras, the distances to the stars Proxima Centauri and Wolf 359 were measured. Unfortunately, the radioisotope generator on board the spacecraft is expected to start running low from 2026, and eventually all the meters will switch off one after another. New Horizons will continue on its way beyond the boundaries of the solar system, and by the year 2038, the distance between the probe and the Sun will have grown to be 100 astronomical units. By that time, the energy generator on board the spacecraft will have stopped operating completely, and it will be impossible to get any connection with it. Following a hyperbolic orbit, New Horizons will exit our system, never to come back. The same thing happened with two other probes, Pioneer 10 and Pioneer 11. They hit an escape trajectory from the solar system a while ago. In fact, they were the first automatic space probes ever to be sent into interstellar space by humans. Spacecraft Pioneer 10. Start of mission 3rd of March 1972. Distance to Earth 127 astronomical units. Speed approximately 12 km per second or 2.5 astronomical units per year. Main goal Jupiter. Mission status successfully completed. Condition not operational. The spacecraft reached Jupiter's system on the 4th of December 1973 after completing a 641-day journey through space. During the mission, images of the gas giant's surface and its largest satellites were beamed back to the Earth, and the planet's atmospheric composition and magnetic field were gauged. In addition, Jupiter was found to emit 2.5 times more thermal energy than it receives from the Sun. The data, unique at the time, became the basis for understanding the makeup of gas giants and their satellites. The trajectory of the second probe, Pioneer 11, through space passed Jupiter too, but its main target was the other gas giant of our system, Saturn. The probe's scientific instruments gauged the planet's magnetic field, and the cameras on board took quite a few snapshots not only of the gas giant itself and its system of rings, but also two of its satellites, Titan and Mimas. According to the estimates, the current distance between Pioneer 11 and the center of our system is around 106 astronomical units. On completing their main mission, both probes continued on their way, moving further and further away from the Sun. Unfortunately, both of them are out of range now, with the last signal from Pioneer 10 received back in 2003. The last signal from Pioneer 11 was received in 1995. Supposedly, both of them are now rapidly moving beyond the boundaries of the solar system. Incidentally, having no chance of ever catching up with either of the two probes we're going to talk about next, the Pioneers were launched at a much earlier date. Spacecraft Voyager 1. Start of mission 5th of September 1977. Distance to Earth 154 astronomical units. Speed around 17 km per second or 3.6 astronomical units per year. Main goal: Jupiter and Saturn. Mission status: successfully completed. Condition: not fully operational. The contribution of Voyager 1 to the Solar System's exploration can hardly be overestimated. It is thanks to this probe that several new Jupiter satellites were discovered, alongside its ring system, which was big news. The Voyager's cameras captured volcano eruptions on Io and provided hard evidence that Jupiter's Great Red Spot is an enormous storm. The probe beamed back hundreds of photos of the largest planet of our solar system and its satellites. After the spacecraft crossed Neptune's orbit, the meters on board sent back a great amount of valuable data about interstellar plasma. Voyager 1 left both the Kuiper Belt and the heliopause behind a long while ago, and is now rapidly crossing the area of the solar system's scattered disk, making for the inner boundary of the hypothetical Oort cloud. It is not only the remotest man-made object in space, but also the fastest of all the spacecraft on their way to exit our system. Being the first space probe to have traveled that far from the center of the solar system, Voyager 1 offered scientists a unique opportunity to study the heliopause. This is the area around our Sun where solar wind pressure and interstellar gas pressure balance. When the charged particles emitted by the star collide with rarefied plasma, elaborate structures form out of elementary particles and magnetic fields. Studying them is crucial for understanding processes taking place in the universe. Unfortunately, by around the year 2025, the power of the radioisotope thermoelectric generators on board the probe will have run out completely, and the connection will have been lost. In 300 years, Voyager 1 is estimated to reach the inner boundary of the hypothetical Oort cloud. It will take the spacecraft approximately 30,000 years to go clean through, and after that it will fly beyond the boundaries of the solar system. 10,000 years later still, the probe will fly by the star Gliese 445 at a distance of 1.6 light-years, and then it will eventually get lost in the infinite depths of outer space. Speaking about Voyager 1, we can't but mention its twin, launched from the Earth on the 20th of August 1977. Voyager 2 had Saturn, Uranus and Neptune for its targets, but it also approached Jupiter for a gravity boost. It's the images taken by this probe that allowed scientists to assume that there are subsurface oceans on Ganymede and Europa. On reaching Saturn, Voyager 2 gauged the gas giant's temperature and magnetic field and discovered several new satellites. It goes without saying that lots of snapshots were taken of both Saturn's surface and its rings. Next in line on the probe's way were Uranus and Neptune. The flyby yielded a great number of unique snapshots, and in total 17 of the two planets' satellites were discovered. Also, it was found that both Uranus and Neptune have ring systems. Under Neptune's gravitational influence, the spacecraft changed its trajectory and left the ecliptic plane. This meant that Voyager 2 wouldn't be able to approach the other objects in the solar system, but it still had other exciting things to look forward to. Thus, the probe was to collect invaluable data about interstellar plasma and cosmic wind, as well as to measure distances to stars and explore the heliosphere. The probe is currently as far as 128 astronomical units away from the center of our system, with the distance growing by 15.37 kilometers every second. It's going to take it around 42,000 years to approach Ross 248, a dim red dwarf in the constellation Andromeda. The minimal distance between Voyager 2 and the star will be about 1.7 light-years, and around 300,000 years since its launch, chances are it will fly by Sirius at a distance of 4.3 light-years. Unfortunately, it is impossible to distinguish such a tiny object from the Earth that far away. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets, like Ross 128b or Gliese 667cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of 3 components. 2 of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The 2 components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with the minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the Sun. Its radius is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri A are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb Telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri b, or Ptolemy, and it also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star. Its surface temperature is reportedly 5,260 Kelvin, or slightly lower than 5,000 degrees Celsius. With these factors combined, the celestial object has an orange hue, and its luminosity is on average twice as low as that of our Sun. Incidentally, Alpha Centauri b emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days, and whose radius measured slightly less than that of the Earth. The suggestion was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts two confirmed exoplanets, as well as at least one hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri b gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multi-layer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation, Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC 2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by 2 crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago, It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. We're surrounded by a great variety of stars, whose light warms countless planets. Their study would be impossible without modern spacecraft and telescopes. It is only thanks to them that we can peer deep into the cosmos to see the remotest corners of the universe. And with each discovery, the world presents us with something new and unexplored, never failing to stun us by its greatness.